first of all, good evening, I guess, good afternoon for the people there, and good day for all the rest. Thanks for inviting me to this beautiful meeting, and it's really a very special occasion. So today I would like to talk about statistical signature of integrable and chaotic quantum Hamiltonians. And really, the Baxter revolution, as was called in 2000, has really affected all of us, and in particular the red notes of Rodney, the book on which we form. Really, we learn a lot of stuff. We learn how to do the sum, how we used to say, is really remain one of the masterpieces, the most influential book in the subject. And in this book, there are a lot of matrices. So today I'm going to talk about matrices, and I will take the point of view of Charles Porter, that in the early 60s called the statistical spectroscopy. So really how to understand, how to spell out what is behind numbers, between a table of numbers. And we can really, if we can really understand the dynamics and whether this dynamics is integrable or non-integrable. This is in particular the questions of today. So indeed, the topics of my seminar will run about the question to be or not to be integrable. And I will spend some times on diagrammar. You will see what I mean by that. Then I will propose a stochastic quantum integrable model based really just on data which come from matrices. And this will bring us to analyze really the genetic code of a matrix, namely what are the main features of chaotic, integrable, or mixture, which is the most subtle one because it's the one that can fool a theoretician if he has really a poor microscope. And then we will see how to find things out, namely how to understand if we are really dealing with a table with matrices which come from an integrable model, or whether we are fooled by some dynamics which has arranged in such a way to look integrable, but as a matter of fact is not. And I will show you two ways of doing that. One which is based on Monte Carlo, is a Monte Carlo protocol, which leads to a decimation of energy levels and somehow filter the integrable component if there are any. And then I will also show that different way, depending essentially on the model at inspection, might be addressed by using higher spacing probability distributions. So this is the group of people that address these people here in Trieste. There is Artur Utsaliuk, which is our postdoc, Andreas Sampige, a PhD student, and Feng He, which is another postdoc in our group. So to be or not to be integrable, this is the question. Well, classically, the story is pretty clear. So when we have a chaotic non-integrable system, essentially we have only the Hamiltonian to deal with. While if there are some regularities, some trace of regular behavior, in particular the most integrable one is when we have a number of commuting quantity with respect commuting well as a zero Poisson bracket, equal to the number of degrees of freedom. So classical mechanics, the story is net and clear and has been solved probably around 150 years ago. Now, the quantum case, on the other hand, is really a pain in the neck. And there is a long list of Cahiers de Doléances, starting, as was noticed already many years ago by Weigert. Because first of all, it's not clear what D is. What is the number of degrees of freedom we are talking about? Is the dimension, the Hilbert space, is the degrees of freedom itself is not clear at all. Now, semi-classically, in the case when we have a system that has the advantages to be also to have a classical analogous, we might use the Dirac prescription to substitute it Poisson bracket with commutators. But this, once again, doesn't solve really the main question of the problem, because immediately we are looking for linear or and functional independent quantities, and how many of them we have to look to state that a system is integrable. Moreover, this quantity has to be local or non-local, because, for instance, projector on any eigenspace is of the energy, of course, commute with the Hamiltonian, but this means that any system in nature is going to be integrable if we assume this definition. So what is really a quantum integrable model? So as I say, this question has made the investigation. I mean, many people have thought about this. So a set of criteria has been laid down. So people say a system, so it's possible definition. A system is quantum integrable if it possesses a maximal number of independent commuting quantum operators. Or we might say a system is quantum integrable pragmatically, if it is exactly solvable. Namely, if we can construct its full set of eigenstate explicitly. Or a system can be declared to be quantum integrable if the energy level satisfies a Poissonian statistics. And finally, a system is quantum integrable if the scattering it supports is non-diffractive. Now, I would start really from this last definition, and I would like to push the idea that essentially the only constructive way we have to set up an integrable model enter if we use this last definition, and moreover, if we focus our attention on a special class of model, which are the quantum field theory, and especially in 2 dimensions. So what I want to say is that if we take the last definition as the one which defines integrable model, namely the scattering non-diffractive, we have really the only way, the only realm where we can have a definite answer to this question is in the case of relativistic quantum field theory. How it comes? Because the infinite number of conservation law that we have in this case forbidden production of decay process, so all the scattering has to be elastic. And then when it's elastic, it has to satisfy indeed the Yang-Baxter equations. And therefore, we have a way really to classify these integrable relativistic models. How to do it? Well, we rely on diagrammar. You remember that in the famous preprint of Toff and Veltman, they set the floor saying that diagrams form the basis out of which everything must be defined. So they define really the operation rule, and then you have not to think anything else, and all should come from that. Now, if I take this point of view, so the rule of the game is pretty simple. I would like to classify, say, all field theory with 2 fields. Well, I will write down the most general Lagrangian, which involve these 2 fields, and then I will impose the so-called integrable sieve, alias find a set of mass and coupling, which make 0 all the production processes. So this is a very well-defined program that can be carried out in simplest case. And this leads to the conjecture that the non-trivial set of solutions, and probably the only one, are essentially the affine total field theory, where the set of masses and the coupling all derive from geometrical quantities, which are the simple roots of the Lie algebra. And for this geometrical origin and many infinitely geometrical relation that this quantity has, this indeed make the theory integrable, alias you can check explicitly that all the production process are zeros, vanished. Well, a part of that, we are really somehow in the desert. So we are as a blind man just walking in a room trying to find out what are other possible example of this type. Now, of course, it depends very much on the starting point. So today, as I said, I take the starting point of matrices. Just for me, system is defined by table. So it's like, to say, the maximum essence probably of Werner Heisenberg formulation of nature. So all nature are encoded in matrices, and I would like to spell out what is behind this object. So I will take then the definition that a system is quantum integrable if it possesses a maximal set of independent commuting quantum operators. Now, it's very easy to see that if the Hamiltonian, the matrix which I take as Hamiltonian H has energy level, which are all different, what happens is that all commuting matrices, which I can find, are functional dependent on H. And the argument is very easy because if all the energy levels are different, I can construct really the van der Waals determinant of all the higher power up to n-1. N is the dimension of the matrices. And therefore, this means that 1h, h square, h n-1 are a completed basis for these matrices. And any object which commute with h is just a linear combination of this object. So in this case, we kill it straight away, the question whether I can have an integrable model when the energy level are all different. And the answer is negative. So this means necessarily a quantum integrable model has to have a degenerate spectrum. Now, in this case, let me go then to the gap of this spectrum, and then I normalize the gap through their mean. Of course, this mean definition is more subtle than what is shown here, but I think the concept is clear. And with respect to this universal variable S kappa, I can plot the distribution of this gap. And the point is whether there is a non-zero probability to have zero gap, namely if there is degeneracy. Now, let's take this as granted. So I assume that I have an Hamiltonian which has such properties, and I would like to convince you that I can find objects which commute with the Hamiltonian, which scale with the dimension of the Hamiltonian in a special way, so there are infinite when I go to the infinite limit, and they are linearly and functionally independent of H. So strictly speaking, I'm defining for you an integrable model. How the story goes. So if I have a resolution delta E for this my histogram, I will immediately see that with non-zero value of P0, I will have many blocks of degeneracy. Now, how many of them and what are the dimensions of this block? Well, the calculation can be done in a probabilistic way. Namely, I will write down the sequence of all this gap, and when there is a degeneracy, there is a zero. So essentially, a sequence of gap is a certain number of certain real number, x1, x2, and x3, which are the values of the value of the various energy level. But when I'm at zero, essentially the two next neighborhood objects are degenerate. So in this way, I can really count probabilistically how many blocks I have of different dimensions. And this is the result, is an exact result obtained from probability. So in this way, I have probabilistic, I know probabilistic how many blocks I have of size 2, 3, kappa, and so on and so forth. So, and this here come the point. So in integrable model, all conserved charges, especially when I renormalize the gap, are on the equal footing. Indeed, I can interchange them and make one of them an Hamiltonian and the other a conserved quantity. So this implies that all the energy level, the level spacing of every conserved charge must exhibit the same level statistics which I find for the original Hamiltonians. Otherwise, I will break this underlying symmetry of all these charges. So this implies that also these putative charges must have a non-zero gap. Hence, at this point, to commute with H and to commute among themselves, to be function independent one from the other, each charge must have the same number of blocks which I computed before, but the only difference is that I have to order differently. So if before there was, say, one block, then two blocks of 3, then one block of 5, and so on and so forth, the other I just have to reshuffle, because essentially the essential role of these charges is to lift the degeneracy of the other charges while preserving their mutual symmetry. So how to do this calculation? Well, very simply, I will write down string of these gaps, which is just, as I say, dictated probabilistically. And then I will order them in a matrices, in a table, once again. And therefore, these energy levels of all this quantity will remain degenerate if in these matrices there is an entire column made of 0. Because this is the worst case where I cannot lift completely the degeneracies. So what is the probability that this event will not happen? Well, it's very easy to find out. Is 1 minus P0 to the n, because this is the probability that in one column all are not 0, to the power n, which is how many of this column I have. And therefore, if I impose this probability to be larger than 1 minus epsilon, at this point, I can immediately determine what is the number of this quantity which I need to lift the degeneracies. And the number of these matrices essentially scale like log of n. Now, what is this log n? Well, it's very easy to understand, because if the Hilbert space grows like q to the L, taking the log of n means that the number of conserved charges, alias the number of matrices which commute with H, commute with themselves, are linearly and functionally independent one from the other, scale exactly like the number of sides. Okay? Okay, now this brings immediately to further question, namely to analyze really the genetic code of a matrices, and is essentially how the energy levels behave in generic chaotic Hamiltonian or integrable ones. Well, in chaotic Hamiltonian, we have these diabolic points, namely this repulsion of energy eigenvalues when they try to meet. On the other hand, for integrable model, we are really playing essentially with sticks that we just throw on the table, and therefore there might be many, many different occurrence and crossing among them. Now, in the chaotic Hamiltonian, there is the famous conjecture by Boygers, Giannoni, Smith that say essentially all chaotic Hamiltonian are related to random matrices. And random matrices, we know there are several types of them. Today, I will just restrict to the so-called orthogonal and unitary ensemble. And the probability to have these eigenvalues lambda 1, lambda n, and these matrices is dictated by this formula where beta can take value 1 for GOE and 2 for GUE. And on the other hand, in integrable case, Berry and Tabor argue in a very convincingly way that the extensive number of quantum numbers which are behind these integrable models make energy levels essentially uncorrelated, in the sense that when you draw the lattice of quantum numbers and then you pose the surface of energy as a function of these quantum numbers, in general, you might have many, many points, completely different one from the other, which has the same value of the energy. So this is what creates clustering. This is what creates really also independence of these energy levels. And once again, to go to this average of spacing, you have to rectify in the spectrum, alias to unfold, as people say. So you take a distribution like the one on the left-hand side, and then artificially you smash and make it flat, defining appropriately the new energy levels as the one which indeed has integer spacing. So in this way, all the energy levels has in average 1 as a gap, and then you can, at this point, compare one to the other. And in the case we are concerning today, we are dealing essentially with three cases. The Poissonian, where the system is integrable, so it's the completely uncorrelated and exponential decay of the gap. The GOE, where has a linear behavior around the origin, which signaled the repulsion, and GUE, which is even stronger repulsion because light goes S squared. So this is essentially the distribution of the gap in the three cases. Now, there is, though, a more subtle and potentially deceptive scenario, which is actually what you meet when you start analyzing spatial Hamiltonians, and is the scenario where imagine you have a poor microscope. In any case, you have a delta E resolution to make all this analysis. And in this case, might happen that the Hamiltonian, now here I depict already in block form, but of course you start with matrices which are all mixed up one to the other. But essentially behind this huge table, there might be sectors which are due, say, to fragmentation of Hilbert space, or simply because you miss some subtle symmetry that probably you have not seen before. And therefore, you are dealing essentially with a mixture of spectrum. So what happened in this way? Well, the situation is pretty interesting, because in this case, you have to do a bit of mathematics to understand what are the distribution of the spectrum which occur when you have a mixture. So you define certain quantities like psi, which is really the probability of having between 0 and x some of the spacing, and finally this EI, which is the probability that the spectrum I does not have any of them in the range 0x. And at this point, when you put all the spectrum together, the density has changed because it has become the sum of the density of each of them. And if you construct this quantity here, at this point, and the fraction of each mixture in terms of this quantity Fi, at the end of the day, the probability of the gap in this mixture situation is the second derivative of this A, which is this expression. So let's see how it looks like. Well, imagine that you have two Wigner-Dyson distribution. The point is, while each of them goes to 0, the combination of the two doesn't. And the story becomes more and more dramatic when you add more and more Wigner-Dyson. So for instance, if I add 20 of them, you see that the curve is essentially indistinguishable from a Poissonian. And moreover, the zero, which distribution, I mean, the value that this distribution has in zero is this one, is exact quantity. And of course, become more and more close to one if I just add more and more mixture. So there is this paradoxical situation that I might have many non-integrable subsystem, but if I'm not aware of this for some reason, and I just analyze blindly the spectrum, I might be fooled and consider the Hamiltonian integrable. So this is the question, how to find out what you are dealing with. So how to identify integrable model from non-integrable ones, just dealing with tables, just dealing with number. Alias, can we determine whether the energy level of H follow a genuinely Poissonian distribution, which are therefore indicative of integrability, or whether we are merely fooled by the superposition of a large number of components which produce an apparently Poissonian spectrum? So this is the question to be addressed. And this question can be addressed, as I said, depending which Hamiltonian you are looking for. And in particular, in the last month, together with the gentleman I introduced you at the beginning of the seminar, we analyze a very, very large class of Hamiltonian based on permutation group in all possible ways, not only next neighborhood, but also including 3-cycle, 4-cycle, and many other combinations. So, for instance, you can define Hamiltonian or random graph, for instance, or you might define Hamiltonian which interpolate between next neighborhood and fully connected. You might do many, 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 many things. In particular, doing that, you met graph like this. So imagine I take one of these Hamiltonians in which I'm playing with coupling constant, putting cycles, putting many things. I diagonalize brutally the spectrum, which typically are the order of millions eigenvalues, and then you find this probability distribution for the gap. Am I in presence of an integrable model or not? Once I took in account all possible symmetry which are behind. So this is a typical situation we are facing. So a spectrum which in all respect looks to be Poissonian, or at least to the best of the analysis look Poissonian, but is really so, or are we simply fooled by this mixture situation? Well, I can propose to resolve this issue two criteria. One is the higher order spacing probability distribution, as I will discuss, and the other one is a Monte Carlo decimation of energy levels. And at the end of the day, in a way or another, you will find out what you are dealing with. So let me just talk briefly on these higher spacing distributions. So we are talking now not only the distribution next neighborhood, but the distribution of energy levels separated by kappa step. So the formula to compute this probability distribution is a universal formula related once again to the probability of having an interval length S in which there are exactly J eigenvalues. And all these probabilities of these many gaps are at the end of the day related to the 2-point functions of the energy levels, which for Poisson, GUE and GOE has this shape. So Poisson is identically 1 and the other goes fastly to 1 when you move in the spacing. Now, this energy level, of course, I can write down as sum of many intermediate gaps. And the point is whether these intermediate gaps are independent or not. Now, if they are independent, as in Poisson, the distribution is easily found just by convolution. And in this case, you can really plot what are these probability distribution for the multi-gap. And nature is that they are centered on kappa. Kappa is the gap you are looking for, but most importantly, the variance grows like kappa. So this means that since the integral is going to be 1 in any case, the right is going to be smaller and smaller and smaller because the curve starts to enlarge enormously. On the other hand, in GUE and GOE, there is very much rigidity of the energy levels. And in particular for GUE, but also for GOE, you can express everything in terms of determinant, where there is this famous sinus kernel. And you can compute it, this quantity, just solving numerically as we did this Fredholm determinant and extracting this spacing. And what you notice is that they are much more narrow because, as I say, the spectrum is very much rigid. Their variance grows logarithmically, but the first approximation is just 1. And therefore has a very distinguished feature, which is different from the Poisson. And what about the mixture? Well, amazingly enough, this mixture has also a determinant, Fredholm determinant formula, which is just the product of all these determinant, because product of determinant is a determinant. In this case, the kernel of the I component just refers to the density of that component. But apart of that, you have everything as before. You numerically compute this Fredholm determinant, and you have this graph. And you see that even though you might be fooled, say, by, don't know, 5 big Dardison, which really looks like Poisson to the first approximation, if your delta E is not very much, is not small, it's enough to do just higher spacing distribution that you immediately see the difference, because you see here, these are the mixture situation, whereas the Poisson is much smaller, okay? However, there is a much simpler way of doing that, which is the following. You take really the distribution of the gap, that might be millions of them, but then you extract a sample of them exactly with the same distribution that you have found phenomenologically. So at this point, let's say you have originally 10 to the 6, 10 to the 7, I don't know, eigenvalues. You extract a large sample anyway, order 10 to the 5, and you start from that. Start in what sense? Well, I have to see whether this number has a possible distribution of a gap in it, and which fraction. So this is done as usually with Metropolis algorithm, namely you extract a number and you ask, do you belong to Poissonian or not? So there is a certain criterion to accept it, and on the other hand, to accept conditionally. And in this way, once you find if there are a certain number of gaps which satisfy Poissonian, you deleted this part of the spectrum, you extract it, you cancel, and you iterated the procedure with what is left out. So if the decimation arrives till the end with the distribution unchanged, the distribution is most likely to be Poissonian. Otherwise, if it stops after kappa step, kappa is essentially the order of the various gap, alias the order of the number of fragmented Hilbert space that you have. So let me show you figures, because a figure is worth 1,000 words. So so this is the procedure I was telling you. So you take your Hilbert space, you take a fraction of it. If you extract it, you cancel, you take 1 over f as a fraction, and you keep going up to a threshold, because you want to arrive to a final situation which the number of level is still large to make statistics, but has been filtered out all the energy levels, which eventually was Poisson. So imagine I start with this, which if I make a fit, best fit really looks Poissonian one. So is really a Poissonian or not? Well, if I apply this procedure on Monte Carlo, the first decimation, I see the curve changes. The second change even more drastically. The fourth is becoming really completely different and has a vanished gap. So the original situation was not integrable at all. What about this? So I start.
You need to come to conclusion.
I'm finished. So if you take on the other end this curve, you keep going, you see essentially all remain the same. So this was really Poissonian. If you have two component mixture, is enough to do just one iteration of this Monte Carlo that you realize that indeed instead was Wigner Dyson. So conclusion and perspective. As Baxter really taught us, discovering and classifying quantum integral model is really a rewarding task. We know there is a lot of consequences for dynamics, to say transport property and many others. So this bring really to analyze the genetic code of the various Hamiltonians and really what is in it. And I show you how you can use high-order spacing and Monte Carlo protocol for distinguish purely from spurious integrable models. And with this tool, we are really making a thorough study of Hamiltonian based on permutation group and analyzing all this space of Hamiltonian, seeing if there is any trace of integrability. And with that, I think the game of integrable model is going to keep us busy for many, many more years. Thank you.
Maybe we have time for a short question. So I might ask, so you're saying that if you take quantum integrable model, there must be degeneracy. If there are no degeneracy, it's not integrable. Am I right?
Yeah.
So any lattice model with study like 6 vertex, 8 vertex, there should be degenerate eigenvalues.
Well, I mean, the degeneracy, if you do not have degeneracy for a matrices of dimension n, any quantity that commute with it is functionally dependent on it. So it's a function of the power of the matrices. Essentially, it's like you are saying the projector are commuting quantum charges. It's the same statement.
Okay. I see there is no more questions. So let's thank Giuseppe.